Hello and welcome to the next part of my platform tutorial in Unity. We've got our character moving left and right, so next we're going to try implementing some jumping. So I'm going to go ahead and open up the code for my platformer script here. The first thing we're going to want to do is add our actual input. Because we're working in two different updates here, the update that happens every frame and the fixed update that happens every physics frame, we're going to want to separate taking our input and actually using our input. And then that will also help us implement fun mechanics like coyote time, where there's an input buffer where there's a certain amount of time that you can utilize the jump input after you've actually inputted it. So we're going to go ahead and make a new variable here, an internal one for keeping track of when we've inputted to jump or not. So I'm going to just call this jump input, this bool. And in our update, which is every frame, we're going to check to see if we have a new input. And if we do, we're going to set that jump input to true. We can't just set it to whatever our jump input actually is, because we might have two update frames set jump input to true and then back to false again before it has a chance to actually jump. So that's why we're using this if statement. We can use it input.getButton as our input for now. Jump is actually a button that's already implemented by default in Unity. If I go to my project settings here and go to my input manager, I can find jump here, so it's spacebar normally. Of course, we can change exactly what this is. For example, we could utilize Unity's new input system instead of this old-fashioned input system, but ultimately all we need is something that will trigger this to then be true. So now that our jump input is true, whenever we press the space bar, we're going to actually want to utilize this input. So down here in my fixed update, I'm going to check at the bottom, after all this stuff to do with moving left and right, if we do have, in fact, a jump input that is true. For these if statements, I could do the long form and say if this equals true, or I can just simply say if and then the variable value, which will be either true or false, and it has to be true for this if statement to be true. In this case, all we're going to do is just simply set the jump input back to being false again. So this isn't going to actually do anything yet because we need to actually jump. So now that we've got our input, we're setting it to true when we input, and then we're waiting to the next fixed update frame to then set it back to false again. Let's go ahead and also jump. For jumping, we're going to add velocity to our actual velocity, which is, our moving X and Y, just like we did here with our rigid body moving left and right. Only this time we're going to be adding velocity to it on the Y axis. The first thing I'm going to do is just store the current velocity of our rigid body in this local new vector 3 velocity, and we'll call it new jump velocity because we're going to make changes to it that will make it our new jump velocity based on the fact that we are now jumping. To begin with, we're just going to set it equal to our rigid body 2D dot velocity. And then once we've made changes, we're going to want to invert this equation so that our velocity is equal to this new jump velocity. So this currently, again, doesn't actually do anything. We're just grabbing the velocity of our rigid body, storing it locally, and then setting it back again. But if we actually make changes to this new jump velocity in between these two lines of code, then this will then get updated in our actual rigid body as well. We want to make comparisons, which is why we're making a new variable instead of just directly changing the actual velocity, because we want to make comparisons maybe between the old velocity and our new velocity. The next thing we're going to want to do is calculate our jump speed. Now, we could just have a hard-coded jump speed, or have one of these variables here be our jump speed. But I want to instead use jump height as our sort of design variable. So I'm going to call this jump height. Jump height. And this is a lot easier to design around. If I have a specific height that the character can jump and no more, then I can design my level around that a lot more easily. Whereas if I have a jump speed that is a velocity that is utilized to shoot the character up in the air by a certain amount, and we use that as our design variable, then it's a lot harder to gauge how to design the level around it. In this case, we're going to calculate how far we need to move up in the air via our jump height. So let's grab our jump height as here as well. Now for this, there is quite a lot of complex maths involved. I have some links in the video. This is a particularly simple but effective explanation of gravity and velocity equations. Essentially what we're trying to do is some really basic projectile motion physics. There's also this video that I'm going to put in the link as well. In this case, you're particularly interested in understanding how these equations work. Our equation is going to be fairly straightforward, but nonetheless somewhat obtuse, whereby we are going to take our jump height, and we're going to try to convert that into a speed. How fast do we need to move up so that we reach a certain height by the time the gravity takes an effect that reduces the initial velocity of the jump to 0, as in to say, once the velocity reaches 0, that will be the apex of the jump. In this case, what we actually do here is take the square root of -2 and we multiply that by our gravity. So if I go ahead and take our physics 2d.gravity, which is just to say the default gravity that will exist that's going to be applied to our rigid bodies in the Unity project, and then we also multiply that just in case, and future-proof this, in case our rigid body has a unique gravity scale, because we're going to muck around with this gravity scale later. So if we multiply this by the gravity scale and then also multiply it by the jump height, this little bit of maths will result in the correct jump speed that is required to get our character to apex at a certain height in their jump. I won't explain this anymore other than just to know that this is the equation that is required, and if you're interested in the specifics of a better explanation, then follow those links in the video description. Now that we've got our jump speed from our jump height, we can then just simply apply this speed to our velocity. So I'm going to go ahead and grab our current velocity, which, we could be moving left and right, we could be moving up and down, we could be falling. We're just going to therefore add to the y of it. So we're going to do plus equals our jump speed. And this will simply add whatever our calculated speed is onto our velocity, which will send us shooting up into the air. So that's enough for now, hopefully, to get us to jump. If I go ahead and save or build that script, and then we go back to Unity and start playing the game. Well, actually, our character won't jump at all if I press spacebar, probably, because we need to set our jump height. So I'm going to unpause the game here so that this gets saved as a change, and then play it again and see. If I set my jump height to 1, okay, that's incredibly high. I wonder why. I'm not sure it should be. Maybe I've made some sort of error here. Let's make sure that we utilize this as a float and not as an integer, in case it was trying to use only integers in the calculation of this physics. So I put the little f beside the 2 to make sure that we're still going very, very high into the air. Perhaps it's simply that I need a lower jump height. So if I do an 0.5 height here, our character still flies very far into the air. Okay, well, I'll revisit this in case I've made a mistake, as the velocity here seems very, very intense, but it could just be classic, Unity values need to be really, really tiny. Let's try 0.1. You can see, maybe it's working correctly. It's just that our velocity is, our numbers are all very strange, and, well, the scale is at 1. Okay. Anyway, the next thing we're going to want to do is make sure that we can actually jump in the air without setting a relative velocity. And this is usually the case for an arcade platformer game. What I mean by that is that if my character is already falling, which is to say they have a downward velocity, and I currently jump, so if I jump at the very end of this fall, you can see that I slow my momentum because my upward velocity is being added to my negative velocity, my positive velocity added to my negative. I'm going up from the jump, but I'm going down from the gravity already. And they counteract, and then my character just sort of stops. And the sooner that I jump after jumping, you can see the faster I'll go up. This is not necessarily the behavior that we want from a platformer. Usually we just want the exact same jump to occur no matter how we're moving. Now there's a couple of different ways we could do this, and some of them are more error prone than others. The simplest way of doing this is just to set our Y velocity to 0 every time we jump. That way our character just stalls in place and then jumps the same amount from a velocity of 0 on the Y-axis. There are a number of errors that can occur because of this, so we're going to do a slightly more nuanced approach of checking what our velocity is and then applying MAS based on that velocity. And this is where we want to utilize maybe our velocity, our old velocity or our new velocity. So before we just go ahead and simply add our jump speed onto our velocity here, I'm going to go ahead and make a new if statement based on the Y velocity of, which is to say our upwards and velocity of the jump. Keep in mind this new jump velocity is just the same as this rigid body velocity here. So we're going to ask, is this greater than 0? Which is to say, am I currently going up in the air? Is the character currently going up in the air? In which case, we don't want to just simply add the jump speed. But before we do that, we're going to counteract the speed of our character. So the way we do this is by taking the maximum of two values, and I'll put it out here first of all. We're going to take our jump speed and take minus our new jump speed velocity.y, or 0. Basically, let's see what the best way of explaining this is. If our jump velocity y is greater than 0, that means that we are currently going up into the air, which means that if we jump again after, for example, jumping, we don't want this to be a compounding jump where we get like a super jump where we jump a bit and now we've still got some of that velocity from that jump, so when we jump again, we jump even farther. What we instead want to do, therefore, is either take our jump speed and take away our new jump velocity, so that our jump speed is reduced by how much we're going to jump, in which case when we do jump we won't get an extra bonus boost. Or if that goes horribly wrong because our new velocity isn't great enough to reduce that value, we're going to just take 0 as our position, so that we just jump from 0 and our jump speed is set to nothing. So if we were going so fast that even jumping would be slower, we don't want to reduce our jump by jumping. That would be really weird if we were going up really fast. So that's why we want to just max this at 0 so that our jump speed doesn't become a negative value we apply. The other thing we're going to want to do is check if the opposite is true, if our new velocity is actually less than 0. Of course, if it is 0, then that just means that we're jumping from a standstill. We're not falling or going up. If else, I think. Oh no, it's not one word. Why doesn't it like this? Oh yes, of course. It's else if. Whoopsie. Let's try that again. There we go. So yeah, this is if our character's falling down. In which case, if our character's falling down, we want to add velocity to our jump speed. We're going to make our jump even bigger so that we compensate the fact that we're already falling. So we need to compensate how much we're falling by. So we're just going to add the math.absolute version of our current velocity. And this time we'll just grab the rigid body velocity in case we have already made changes to our velocity. So we're going to go ahead and grab our y velocity. By getting the absolute value, that basically just means that if this is a negative value, which it will be in this case because we're going down, like -2, we're going down by 2 every frame. This will turn this into +2 instead of -2, and then we'll add that 2 onto your jump speed. So then our jump speed will negate this jump, negate the fact that we're falling, and then add on the jump again. So basically this whole thing is to try to make sure that no matter if we're falling or if we're already have an upward momentum, our character will then jump and reach the same height. And you can now see that perhaps this is a frame rate issue I had before that I'm now circumventing, where our jump input is getting set to false. Now that we've set our jump code up correctly, I can maybe change this jump height back to 1. Oh, I know. I think I know what it might be. Is it because I used get button instead of get button down? Ah, this is what it is. So this is a crucial difference here, where get button is going to be true every frame you hold down the jump button, whereas get button down is only going to be true the first frame after you press the jump button, which basically means that that's why my character is flying up into the air, because I was holding down spacebar. Even if I was only for a few frames with high frame rate, it would then speed up into the air. So now I should change this to get button down, and our value should be set at 1. And now, of course, we can change this height later. And now, even if I'm at the very bottom of my falling, so if I jump a bunch of times and then begin to fall, and then I just jump at the very end, then our jump should be the same consistent jump height, no matter what the situation is that we are in, whether we're falling or we're already going up into the air. All right, well, we've sort of future-proofed double jumping a little bit here to make it feel nice, but we do want to make sure that we can't just jump as much as we want, so we're going to have to utilize some kind of ground check. You've maybe used a couple of different ground checks by now to make sure that our character is on the ground. There's a few that you can do. Some are more complex than others, so I'm going to utilize something that's a little bit more complex this time, perhaps, than I have before, but hopefully it'll be a bit more foolproof as a concept. So this time, instead of making a variable that we check every single frame, we're just going to make a method which has a return value of a bool. So we're going to call this isOnGround. And this way we only actually check if we're on the ground for computational, to make it more efficient. Every time we need to know if we're on the ground or not, say, for example, if we jump. Now, for us to return if we have a return value of a bool, it's going to give us a red error until we actually have a return value. So for now, I'm just going to say return true. This means that, it's just going to be that we are always on the ground. It's going to, every time we say is on the ground, it will just return true. Let's go ahead and make sure that we add our if statement here so that we can only actually jump if is on the ground is true. So basically the sequence is we're going to have an if statement. This method is going to get called. It's going to return a value. In this case, it's just returning true for now. And then only then will the if statement be true as well. Notice how we are actually putting this if statement inside the jump input. And in fact, I'm going to also stick this in here as well. This means that we can still use up the jump input even if we can't jump. So it won't just keep waiting until we can jump and then jump. Though this is something that we might want to iterate upon later for our input buffer. Anyway, let's actually check if we're on the ground. There's a couple of different things we're going to need to do, but fundamentally we are using raycast_hit 2D, and we're going to create a raycast_hit variable, and we're going to set it equal to physics 2D.boxcast. What a boxcast is in this context is a box that's going to be a rectangle similar to the rectangle that a collider contains. With this box collider 2D, except we're just going to check if anything collides over a particular square. So the method arguments that are going to be required for the box cast, there's a couple of different ones, and we're going to base those off the collider that we already have so that we can just check basically, is there anything colliding at the bottom of this box collider? So we're going to take the values of the size and shape of our box collider at the bottom from the box collider that we already have. So let's go ahead and make a public reference to that. So I'm going to go ahead and create a box collider here, box collider 2D, and we'll call this U box collider. And while we're here, I'm going to go ahead and also make a layer mask, because we're going to only want to test if we are actually on top of a platform. We're not going to just be able to say, oh yes, we're colliding with something. For example, we could be colliding with the character itself, but that's no good. We have to be colliding with the platform to be considered on the ground. So we're going to need a layer mask for that. So we'll call this platform, let's try that again, platform mask. We'll call it U platform mask, since we're going to have to set it up in Unity. Okay. So if we scroll all the way back down into our box cast, we're going to need a 2D origin point. Well, that's just going to be the center of our collider. So if I go to my collider and do bounds, we're going to access the bounds of our collider, which is the actual collider dimensions. And those dimensions have a couple of different variables we can plug in. For example, the center we can plug in as the origin point of where we're going to start this collider test. Next, we're going to need, let's see, what does it say? We're going to need the size, which is going to be simply just the same thing again, box collider dot bounds and dot size. Next, we're going to need an angle. In this case, we don't want to rotate our box at all, because we're just going to check underneath it. So the whole thing's going to shift down, but we're not going to rotate the box, because that would be really weird in this context. We're going to say 0, so no rotation basically. And then the direction, so what direction is this box going to be shifting as we test if there's anything that it can collide with. In this case, we're going to just use vector 2.down, because our character is always going to be testing underneath them. Finally, we're going to need a distance. In this case, our distance is going to be absolutely minute, because we're only going to test directly underneath the character. So we don't want to, like, for example, test, is there anything down below here or here? We only want if there's something directly underneath them. So I'm going to go ahead and just create another little variable, because I do like having things be variables rather than hard-coded values. In this case, I'm just going to call this a public float extra grind check height, extra grind check height. Let's make that U as well, because we're not going to change this as a design consideration really. We're just going to set it as a particular value and forget about it. So we're going to set this as our extra grind height. Now, the last thing we're going to add is our mask to make sure, where's our platform mask, to make sure that we're only checking if we collide with the platform. We're not including, for example, enemies, unless we maybe want to be able to jump on their head. I don't know. But we can decide to do that with our mask anyway. So anyway, we've got this raycast hit, which will contain now all the information that this method has shot back out at us. It will shoot back a raycast hit 2D, which is the variable type here. So now we can ask it questions. We only actually care about one thing, which is, did it collide with anything? So we can just say collider is not equal to null. Well, this will get us a value, and we can take this value, either it'll be true or false, and we can use it as our return value. So if it is equal to null, it'll be false, and if it isn't equal to null, it will be true. So if it's not equal to null, that means we did collide with something, so it's true, which means we are on the ground. And if it's false, we'll return false, which is to say we're not on the ground. So now I'm going to go ahead and save that, and hopefully all these values will show up in my script. So for example, the box collider, we're going to have to drag that in here. Our layer mask, we'll set that in a moment. The extra ground height, I'm going to set at 1.0.1 maybe. Now the mask, we need to set up the mask actually for. So I'm going to click on my platformer. Sorry, my platform. I'm going to go to my layer and add layer, and I'm going to add a layer which is for platforms. Then I'm going to reselect my platform and set that layer to the platform. I think I've misspelled that. Oh well, whatever. And now, so long as it looks consistent, it doesn't matter. I can change it later. We're going to set our mask to platform. So this mask is now saying, the only thing we're going to check for in our collision are things that have this layer mask ticked, which is the platform. So now if I run the game, hopefully our code will work. So I can jump. If I span spacebar, I can only jump while I'm on the ground. That'll be all for today. Have a go at changing the jump height of your character to see what feels right for your platforming. We'll be adding lots of other stuff, but we've got the sound fundamentals here of platforming. Oh, wait, there's one thing that I need to quickly do. I've realized if we have a wall at the moment, so if I duplicate this platform and rotate it by 90 degrees, oh, not 90 degrees on the y-axis. Is it the z-axis? Yes, it is. If we rotate this and put this here, for example, I think that we might be able to jump up the side of the wall. Yes, we sort of. Well, we can't, but let's make sure. Yeah, I did it there a little bit. So it's possible in a very specific frame. And the reason for that is because our collision size is exactly the dimensions of our character. And, you know, that could technically be collide if it's right up against the wall. The collision might decide that, you know, this is overlapping that. So just to make sure that that doesn't happen, we're going to just modify the size by a new vector 3, a very tiny new vector 3, which will just be a very small value. Let's say, for example, 0.1f on the y-axis and 0, 0 on the minus 0.1 on the x-axis, which is to say our left and right axis in the 2D space. Nothing on the y and the z. And this just means that our collider check will be very slightly thinner than it is tall and wide. Sorry, tall and... No, there only are 2 dimensions. Slightly thinner than tall. Which basically means that when we're right up against a wall, we shouldn't be able to jump up the side of this wall. Though that's exactly what I am currently doing. I wonder what's going wrong here. Maybe I've got this the wrong way around. The size... size minus vector 3. Oh, of course, I'd made a double negative because I said minus a minus. Whoopsie, which means we added to the size. So let's just make this a positive value and then take away from it here. But I kind of demonstrated the problem by making it worse, as you do. Let's try again. Yay, now I can no longer jump and collide with this. All right, I think that might be all for now. Let me just make sure. Did I do physics materials already? Yeah, so we can do that lovely slippery zero friction. All right, I will see you all in the next video.